Ladies and gentlemen, in this lecture I would like to explain to you the calculation of surface runoff. In this lecture especially with the SCS method, which is the Soil Conservation Survey from the US Agricultural Department. So this is a special method which could be seen as a standard calculation method to get the surface runoff from a certain precipitation event. But why should we look in detail on surface runoff? Surface runoff is always negative. So when we have surface runoff, we can have on the one hand flooding. Surface runoff is mainly connected to flooding, otherwise rainfall would go into the groundwater or would infiltrate into the soil. When this is not the case, then it goes to the river. It starts as a rainfall, will be transformed in surface runoff, goes to the next river, and then the river makes flooding, let's end. And on the other hand, surface runoff has a negative importance because it is mainly responsible for erosion, for erosion of soils, for the loss of soils which cannot be used in agriculture anymore, because it is eroded to the river and then transported downstream to the next larger river and then to the ocean. So surface runoff is always of negative importance, and therefore we should calculate it in order to avoid it. So first of all, I would like to look on the precipitation and how we go from the precipitation in something like a conceptual model to the surface runoff. We have some precipitation which goes to the vegetation, and there it will be captured by the vegetation, will stay there, will be again go back by evaporation to the atmosphere, and therefore not all the precipitation is going to the bottom. There will be a loss due to interception, which is the loss of precipitation in the vegetation. And this precipitation which goes directly or which goes after interception to the surface of the bottom is called the effective rainfall, and this effective rainfall can be calculated by the intensity of the rainfall, which is here minus the interception intensity, and this is always something like a height. When this is the rainfall height per hour or the rainfall height per day or whatever, then this is the interception rate per hour or the interception rate per day, and the remaining between rainfall on the one hand and minus interception on the other hand is the effective rainfall, which comes finally to the ground. When it reaches the ground of the surface of the bottom, there can be two processes. First of all, there can be infiltration into the ground, or there can be, if infiltration is not possible, there can be surface runoff, which then goes directly to the next small creek or whatever, or to a river, dependent on the size of the next free surface flow. So this then is surface runoff, and we want to calculate the surface runoff from the precipitation or from a rainfall event. So the first thing what we have to look at is something that we have a pool or puddle or whatever of rain. So, and this free surface of this pool can be calculated by the effective rainfall minus the intensity of infiltration. So if there is a large infiltration, then when the infiltration is larger than the effective rainfall, then the surface of such a pool or puddle goes down, and when there is larger rainfall intensity, then there is infiltration intensity, then the height of the pool increases and the pool gets larger and larger and larger. And when it reaches a certain height, for example here this height that it can flow down this small walkway, then we have also surface runoff, which looks like this. So then we can calculate the surface water lying on the surface of our soil or of our bottom as effective rainfall minus the runoff, which can be seen here, minus the infiltration which goes into the bottom, which goes into our soil. So this is the equation for the free surface elevation of such a puddle, pool, or how you call it, and this is very important. In the next step, we look for stationary conditions. Stationary conditions are always helpful, otherwise we have to solve differential equations. This is a differential equation. We can solve this very easily with MATLAB, but in simple hydraulics we only look at stationary conditions. We say that the water height of this pool does not change anymore, and therefore this left hand side is 0, and then we have the infiltration rate is the effective rainfall minus the surface runoff. So this is the infiltration rate, and the effective rainfall intensity is the actual rainfall intensity minus the interception intensity. Yes, in hydraulics we always look at heights, rainfall heights per day or whatever. This means that we have to integrate these equations, which the dot means always per time, over the time, and when we integrated this equation, for example, over 1 hour, then we get something like the total infiltration rate, the total rainfall height, or the total interception rate. So integration here just means cancelling this point here everywhere, this dot, and then we get this equation. The rainfall, infiltration rate is, or the infiltration height now is the rainfall height minus the interception height, which is the effective rainfall height minus the runoff height. So this is the first equation. We need to calculate the runoff. We want to have the runoff here. And the second equation comes from the so-called SCS model. The SCS model has some simple assumptions in it which are very helpful, which are not absolutely correct, but they are working very well because the parameter in this model are chosen in that way that this simple model works very well. It comes from the simple idea that the runoff is proportional to the infiltration. So the more it rains, the more there is runoff, and also the more there is infiltration. So it starts from this assumptions, but this assumption is not really absolutely true, because runoff and infiltration is something like the sum, or it has to be summed up. It's not really, it must not be always be proportional to each other. But this is the basic assumption of this model. Runoff is proportional to infiltration. A lot of runoff also means a lot of infiltration. So then the runoff side is made without units by dividing it by the total effective rainfall height. So runoff by the total effective rainfall height, which is this, is proportional to the infiltration rate. And finally, we make this proportionality to an equation by inserting something like a proportionality constant, which is called SS. Here the infiltration rate is this proportionality constant times runoff rate divided by effective rainfall height. So now we have to get this proportionality correct, then the whole equation is correct. And actually the United States made a lot of experiences on this parameter, and they have a lot of data on this, and this model works very well because this parameter is very well investigated. So when we put this equation together with this equation we just derived before, saying that this is the same as this, then we can skip the infiltration rate, and we get the runoff rate is the effective rainfall rate squared divided by this proportionality factor plus the effective rainfall height. In this way we only need the total rainfall height and the interception rate, and this parameter to get the actual surface runoff height. So what we need now is this S, and this S is more or less something like the permeability, and this S is calculated by a so-called curve number, which is here. Here S can be calculated by this formula in this model, and here this is the curve number. Let us show how the curve number works. So when we have a curve number of 100, then there is 1000 divided by 100 is 10 minus 10, then S is 0. When S is 0, let's look in this equation, then the surface runoff, the runoff rate is the same as the rainfall height. So everything goes into, every rainfall, every effective rainfall leads to runoff. So this is the equation. Here is the rainfall height, and here is the effective surface runoff. So when we have something like 60 millimeter a day of rainfall, then we have actually or 50 millimeter per day of rainfall, then we have actually 50 millimeter of surface runoff. So everything goes into surface runoff. For Cn is equal to 100. So a soil or a bottom with a Cn of 100 is something like concrete. There is no infiltration on a soil with a Cn is equal to 100. On the other hand, when we have small Cn values like 40, then you can see here, let us think of a daily rainfall event of 150 millimeters per day, then we have only 10 millimeters of surface runoff. So a soil which has a very low curve number leads to something like very little surface runoff. Such a soil is very permeable, and a lot of groundwater is formed in such a soil. So this is the idea behind this theory, and this idea works very well. So the last thing what we need is, or next what we need is, what is a curve number? And there they have a lot of tables to determine the curve number, a lot of parameter. So this curve number of course is dependent on the land use, which in this table is this row here. Here you can see the land use, crop, forest, whatever, grassland and so on. And on the other hand on the soil texture. So and the soil texture is here. They distinguish 4 different kind of soil groups, which is A is a soil from its texture with a very good permeability, and low down to D, which has a very low permeability. So we can have something like a forest, but on something like a very permeable soil or on a very impermeable soil, which is the number here. So when it's permeable, very permeable, this forest, then we see the total curve number is 25, which is very, very permeable. And when the soil itself is impermeable, but we have forest on it, then we have a 70-70 here, which is a very, very impermeable, or quite an impermeable soil. So this is the idea behind it. There are other parameters which can determine the curve number, but that's enough for this lecture. So the next thing what we need is the interception rate. So this formula is done when we have here the interception height, and the interception rate according to this theory is directly connected, oh this must be IC, is directly connected to the to this S parameter. So 20% of this S parameter is the interception height. This is found out from data, or from looking carefully at data, and therefore we have also now the interception height. This is not evapotranspiration, it is interception here. We can get this from this formula. And when we introduce it here, this interception rate, then we get again the surface run of everything. When we know this S parameter, everything is done. So that's the idea behind it, and now we have to make some exercises to really understand it.